Okay, now that we have our glorious arrangement of lithium-ion batteries, the question that we always ask ourselves in the concept of technologies, how do we make it better? So to make it better, we have to consider point by point sort of every component that we have in the battery. So it was an issue figuring out what to chain, but now that we kind of know what to chain, on the basis of what works, what can we improve? So the anode, we know it's lithium intercalated in graphite. We know that the capacity here is limited. So whereas if you were to have lithium metal, you will have 100% lithium constantly available. This is lithium C6, so there is one lithium for every 6 carbon atoms in your intercalated structure. And it tends to have a bit of an issue putting stuff back inside. So it is much more common that there will be a surface affinity, so stuff stays on the surface, than going inside and actually intercalate. This is an issue of the energetic of the whole process. And also you have the solid electrolyte interface, not necessarily a problem depending on how you use your electrolyte, but you need to remember that it's a thing, it's there, it exists. So the alloys can be back at this point. We could introduce our lithium into something else, and our very notorious nice and face center cubic alloy structure of silicon, tin, antimony, stuff like that, alloys that have these type of spaces in between, and this is sort of a 3D network in which the lithium could move within these empty spaces. And it will have a very large capacity because you should be able to put a lot of lithium inside, and since you don't have the plating, so you don't have the lithium that goes first on the surface and then more slowly inside, the charge should be faster. This has been explored by Tesla some years ago. The main issue, as you can probably guess by the image here, is that this thing has a huge lattice expansion, like enormous lattice expansion. So evidently you cannot work a battery in nice and solid and compact form if one of your components is expanding of 300% every time you completely charge it, because it means that it will crack every component that you have, and you cannot keep the contacts in one form as well as you do with the others. You risk issues. This is not exactly what you want. The difference of lithium and the alloy in terms of potential energy means that, first of all, you still have the solid electrode interface, and you rob the lithium away from the alloy, even though when it goes in at crazy degrees, and you can actually intercalate a lot of lithium in. You still have this issue of you rob it away from the surface, and given apart from the expansion problem, given this issue of putting the lithium inside, you cannot do the fast charging of your battery. So if you're using it for cars, which are going to need a huge volumetric volume of energy to be able to work based on a battery, you need the charge to be fast. So you want a lot of energy, electrochemical energy, to be stored in your device as fast as possible, because no one wants to wait 24 hours for the battery to be charged. You want it charged fast and immediately operational. So at the state of the art, you still tend to use stuff that is like carbon-based ish with intercalation. Of course, the question could still be, at some point, if we can go back and use lithium, we will very much appreciate it. Second perspective that we want to put is the perspective on the making of the cathode material. And this is a very big perspective, not only because these structures are absolutely beautiful, but because by nature of being this beautiful, then we have this game that we can do, and every time we need to figure out how a structure is arranged, we need to put all of our chemical insight actually in place, not only in terms of what oxidation states are stable, where are the energies, what are the sizes, what are the possible structures that we achieve. Now, as we were discussing before, the first thing that you need here is that the planes in the structure, if you use the sort of like the so-called O3 structure, which is this thing with layers, you want the order to be as optimal as possible. So your octahedral cation, which is your metal cation, transition metal cation, must not be or must not like the same tetrahedral position that the lithium will occupy. So this nice type of order will only work depending on the sizes, the reciprocal sizes of your cations. So by this nature, if we were to be able to use sodium plus, this will order better than lithium, and the cobalt orders better than nickel. So that's also one of the reasons why you use cobalt, like lithium cobalt oxide as your cathode material, and you don't use nickel cobalt oxide. Nickel could be better for sourcing reasons, but it doesn't order that nicely. It has a limitation on how much lithium can you actually put inside before you start getting disorder. And there is one thing that you need to be careful with. So if you remember the scheme of energies that we saw before, the redox couple of cobalt 4, cobalt 3 is very, very, very close to the top of the oxygen 2p band of energies. And this is also relatively close to the nickel 4, nickel 3. So this means that on top of the issue of the ordering that nickel tends to have after a certain level of lithium insertion, this closeness, when you are at a certain level of potential trying to completely discharge the battery and stuff like that, when you have a certain level of lithium which is too much, you might bring this potential way too close to touching the oxygen 2p band. If you touch by electrochemistry, by the voltage that this thing is filling, if your oxygen 2 plus top band becomes the one that is in chain with this whole series of electrochemical potentials, you will evolve oxygen. So your battery, instead of doing electrochemistry of intercalation, detercalation of lithium, and as the lithium goes in and out, you create electrons, it will start to basically react away in the structure and basically make these oxygens over here clamp together, go out as oxygen molecules. Not ideal. This thing can be stabilized if you put stuff like, for instance, aluminum 3 plus. With 10% addition, you stabilize this thing, this interface gets nicer, but the more stuff that you put that is not involved in the electrochemistry of the redox couple and inevitably chains with how much lithium can you accommodate in the structure, because if aluminum 3 plus cannot have different oxidation states, then nothing is compensating the charges of lithium plus entering the structure, so there will be less lithium to be able to accommodate. And you need to remember that once you take it in and out of your structure, so you have your lithium, your oxygen, your metal, depending on how big is the affinity of your transition metal for the other coordination state, when your cathode is almost completely discharged, so there are a lot of vacancies in the in these states in between where lithium will be, it could very much be beneficial for the structure, not for you, but the structure might like it, for the metal to occupy this empty tetrahedral site. And if the metal goes in there, then you change completely the coordinations and you might have distortions within the structures. So this is something to be mindful of, and that's the reason you don't use each and every metal that ever worked the periodic table. You need to use metals that are able to stay in the structures. Not all of them can do that. Not all of them can do it from 0 to 100%, and you need to be able to chain the energies properly. This thing is in 2D conduction, so the lithium conducts in the plane of your intercalation. If you want to do transport fast in 3D, this structure cannot do this, because 3D will require you to go within the layer. So within the layer is not something that this structure will allow you to do, especially because you want to keep the very nice ordered structure. So you need to move to another type of structure. So from one very beautiful solid state structure to another very beautiful solid state structure. One thing that you can do is use the spinel structure. So the spinel structure, as you can see, is a completely different arrangement. So you have this face center cubic material with these chains of like corner sharing, edge sharing octahedra, chaining in 3 dimensions. And what is not an octahedron is a tetrahedron that then is actually corner sharing with the octahedra. This thing can be done with manganese, for instance. So depending on the charge and discharge, you occupy increasing levels of these spaces in between. So between 0 and 0.5, the lithium is in the tetrahedral site. At 0.25, you end up with half of the tetrahedral site. With 0.5 to 1, you go also in the octahedral vacancies of the structure. And you can go back and forth and back and forth, and this is your red scalpel. So you want the metal 3, metal 4 to be able to accommodate this difference of lithium occupancy in, and this will be the thing that allows you to do electrochemistry within the structure. This is sensitive, so they chain with each other, but when they chain, you need to remember that the metal also has opinion. So depending on what you have as your transition metal, you want to be able to keep this voltage at 4. So the specific capacity will be a function of the lithium going in and out. So if we have manganese as your transition metal in here, nice at a certain level, so you can go basically from 0 lithium with manganese 2 or 4, close to here. You start to add lithium, you get to this point of lithium manganese 2 or 4, but you can see that whereas here you have like your 4 voltage and specific capacity, this will go higher in specific capacity because you are increasing the level of lithium that is inside. But at some point you see that, experimentally speaking, the voltage drops. So if you keep adding lithium inside, something is happening in your structure that drops the voltage. So something is changing in the energy states. Now this is the trick of the fact that this is solid state, so things happen. So this is a 0.25, 0.5, a 0.5 drop in voltage. When it drops from 0.5 to 1, you end up having a 3 volt, not 4 volt. So this would be a huge change in your battery line. Imagine if I were to tell you, okay, your device is operating, but if the battery is 50% capacity, remember that the voltage is different and the operation of the circuit of your cell phone will have to be different. This is madness. You cannot use this. Like, it needs to stay stable at the level you want it. The question is, why? What's going on? You're still putting lithium inside, so it's not the lithium the problem. The intercalation and intercalation is working properly, but this change in voltage is coming from the structure. This is coming from the fact that fundamentally that we're using manganese 3 plus. Now we want to put manganese 3 plus, which is a 3D4 metal. We want it in octahedral coordination, and it should stay in octahedral coordination so that the lithium can do its merry way between tetrahedral site and occupy then the octahedral vacancies, be happy. So 5 d orbitals, as usual. But we know that in octahedral coordination they kind of sense a slightly different energy. So instead of having 5 degenerate orbitals, you end up with a split of 3 orbitals and 2 orbitals on top. They are relatively close to each other. So when you have your 4 electrons, you still apply hand rule Pauli principle, 1, 1, 1, 1, and you have this configuration of all of them going through. Now, the issue with this thing is that this thing has a series of energy levels that are exactly the same, right? So, it's not that it can stay like this, but not necessarily, because there could be a point in which it's beneficial for the structure to try and remove this redundancy in energy. Why are all these orbitals all at the same energy and all equally feeling the same coordination if we could do something different? The something different here relates to changing the coordination environment. So you have bond elongation, bond compression. This thing is called Jahn-Teller distortion. It's a thing in molecular chemistry that some of you might have countered. In solid state chemistry, Jahn-Teller distortion is still a thing. So with enough manganese 3 plus, you have a full distortion of the whole business. Even at room temperature. The issue is that the distortion of one of these octahedron is, statistically speaking, the distortion of a sequence of octahedron, and they all distort in comparison to each other. So when you distort something in solid state chemistry, you really crack the whole structure. So it's not that the structure is not crystalline anymore, it's just that it's not in the right shape. So in the other shape, you have the 3 volt energy gap. So you are changing the energy gap because the energy of the states of your metal redox couple is changing. It's changing because the metal redox couple is changing coordination. It decided it didn't like it, it just rearranged. And you cannot stop it. You want to put lithium inside, fair enough, we will sense something different and the metal will become Jahn-Teller active, and you call it a day because there will be a benefit in changing the distortion. The distortion will propagate through the whole structure, and that's it. So this thing is a limitation for manganese, but in itself the spinel structure can still be a good idea. So remember, not manganese in this metal, otherwise you have an issue. But when you have the right metal, you are at 4 volt. In some cases, if you are using a 3-4 Jahn-Teller active redox couple, you need to stay between 0 and 5. So you need to limit yourself with how much are you charging and discharging your material, because otherwise you know that you distort the structure. So this manganese will do it with the amount of lithium. Can you stabilize this? So can you make sure that this avalanche of Jahn-Teller distortions distorting the whole structure and changing the voltage doesn't happen? One of the many things that we like to do, throw another atom in, see if it stabilizes the whole business. So instead of having 2 manganese 3 plus, you could have the same charge distribution, so something that is equivalent in terms of stoichiometry of charges, but different in terms of stoichiometry of materials. So for 2 manganese 3 plus, you can have a nickel 2 plus and a manganese 4 plus. The manganese 4 plus doesn't have the problem of distorting. There is not this voltage teeny tiny step at 0.5 as the regime changes. Since you have lower manganese 3 plus concentration because you doped with nickel, then you don't distort the whole structure because of this Jahn-Teller thing. The capacity will fade a bit upon cycling. What couples can you possibly use as redox couples? You need to remember you cannot go 5, 4, because manganese 5 and 4, they have the oxidation states available, but they are overlapping with the oxygen 2p energy, so you will be doing electrochemistry on oxygen, not our scope. The nickel 3, nickel 2, nickel 4, nickel 3 are accessible, and if you manage to do this trick, then you can have a battery that works at 4.75 volt, so not even bad. So if you have this composition like this, so we were discussing, put half nickel and then the rest is manganese, there is one mobile lithium every 2 cation. So here, given where the voltages go, whereas before we were always wondering about what is the anode in comparison to the LUMO of the electrolyte, in this case you have the trick of the slight difference between the HOMO and the cathode. So instead of having a solid electrolyte interface on the anode, you end up having a solid electrolyte interface on the cathode. So this limits a bit the efficiency, because again you have this issue of the electrolyte interface sort of pacing and sometimes sequestrating the lithium, not exactly ideal. Another option is to basically have the same business but with lithium and titanium. Titanium 4, titanium 3, we saw what it is as couple, so it is accessible. There is no solid electrolyte interface. This is squarely between the window. The limit here will be the voltage, because you reduce the voltage inevitably, but it doesn't fade. It doesn't fade. You can do a lot of cycles, so it's perfectly stable. Why is it beneficial in comparison to other batteries that will operate at the same voltage? That this thing will have a significantly lower fabrication cost. So if it's a significantly lower fabrication cost without issue of decomposition, evolution, redox, unwanted stuff, then fair enough, could be worth using. But worth using means also that we need to think about the high performance battery things. So for a car level, you want a very high voltage, a very huge charge density, especially of the cathode, and a huge intensity of the current that you're able to pass through, because you need to operate a whole car on a battery, which is not something that you will usually do, if not for the fact that we want to do sustainable energies, right? So if to compete with a combustion engine, you need to raise this series of parameters, right? But the voltage limit is imposed by the top of the oxygen 2p band when you use oxides. How do you tweak the energy of the oxygen 2p band? If you have a stronger covalency in which these oxygens are actually involved in, then this will drop. So at the moment, this will go into what are you using in terms of structure, right? So if you have your oxygen involved in a bond like silicon O4 something minus phosphate sulfur, the covalency of those bonds is so strong that it will drive down the 2p band, and on the other side you want a very strongly bonding cation. So this thing, can it be done? It can be done. Can be done in structures that are not the spinel and not the O3 layered structure that we saw before. Something like lithium iron phosphate, right? This thing becomes an olivine. So the bond of the oxygen with like the counter cation in this case is much stronger. So you have, in this case, iron is under coordinated, so it has a lower arrangement of coordination in comparison to what it could potentially do. And you have the redox couple of iron 3, iron 2, which goes a bit higher. This is another battery that can really cycle nicely. And here you need to remember that the lithium is in 1D, because it cannot go through a whole plane, it can only go through a single channel in and out to the structure. These materials are super nice, iron, phosphate, everyone likes them, you can find them everywhere, cool. And it will go at 3.5 volt versus lithium, which is a perfectly operatable voltage of a battery, almost at theoretical capacity. So the open voltage and the one that you actually get is real. But since we are going in channels, like in only one specific direction, it means that your cathode needs to be prepared in a way that optimizes this crystallographic orientation. So you tend to do this with like oriented nanoplatelet, but this of course adds steps to the actual synthesis method. So the coating would assure the maximum conductivity, but to do the coating, then you need to add an additional step. And the quality control of this thing, since you wanted such a precise microstructural control, so you built your structure, how is it actually arranged, will add steps over steps of quality control of the electrodes to make sure that this thing that you just made is exactly equal to the previous one. So, summary on what we have on the cathodes. This one is the one that is usually used. The lithium cobalt oxide is the one that you find in most batteries, which can stay basically between 4 and 4.5 voltage, charging, discharging completely, and no one cares. Nice. Then you have the one that we just saw, which is the olivine, which is a lower voltage but perfectly stable, perfectly flat, amazing. Then you have the spinel thing that, depending on are you using nickel to substitute it or not, you will end up with voltage drops, or you will stay stable at the right voltage with the known issue that we already discussed. The last perspective, which is super tricky, so we're not going to spend a lot of time on it, is the perspective on the electrolyte, because as we discussed, if you want to have a 4 volt or 5 volt system, anode and cathode chaining are something that also require the electrolyte in between to be chained properly. So at the state of the art, the current electrolytes are still based on basically lithium salts that are soluble in organic solvents, right? So you have the carbonates that make you that trick with the anode, and you put these salts in so that when the lithium plus comes out, it actually has something to coordinate. It could be interesting if we could manage, because this thing still needs some sort of like slushy liquids. They're not liquid, but they're still like this sort of goo that you don't want to get out, but it needs volume in your structure, right? If we could have a perfectly crystalline, so another solid, as the conductor of lithium that separates anode and cathode, you will have a fully solid state battery. Super interesting. What is potentially the problem? So having a solid will block the dendrite thing, because the solid will give a very precise point of contact and point of in and out with the lithium. So lithium could potentially be a solid by itself, right? So you could use fully metallic lithium, because if you don't grow anything and it goes smoothly in and out, then it's fine. But the needs for this thing are very complex, because you need a conductivity that is high, so you need to be able to get lithium through a solid structure fast without any interface in between that is not a solid. Everything is solid, right? Needs to be chemically stable, mechanically robust, but possibly flexible, because you need to arrange your structure, and you need to have it electrochemically stable as well, so it must not reduce, oxidize, not conduct electricity and stuff like that. This is a very complex mix, and ceramic polymer composites is a very tricky point. So doing polymers and doing ceramics are two different disciplines. Doing a mix of polymers and ceramic is sort of like state-of-the-art approach in which two disciplines that don't really touch each other could potentially try and see if something is going on, but it's very challenging for every scientist involved because the necessities are inherently different. First of all, in the synthetic approach. A possible example of something that could work as a framework to conduct lithium are this thing, like these huge garnets. So you have a lot of different atoms chained with each other, but one of these is the lithium, and in the way the garnet is arranged, you have lithium occupied, empty, occupied, empty, and it can go through the structure in 3 dimensions, so pretty cool, high 3D mobility at room temperature. But the issue with structures like this, and the reasons why you might want polymers going around, is that you need contacts within this thing, and you need to stay within all of these limits. So the electrolytes and the cathodes, and possibly something to do with the anodes, need to be chained together for a new high performance battery. So super quick summary to remind ourselves what is really important in this business. A battery is a group of interconnected electrochemical cells. That's it. So what you're doing is you want to store a lot of energy in terms of electrochemical energy in a very small volume. So you want the cost of the materials to be low, the energy density per weight to be high, so you have a battery with a lot of energy, but that it's very, very light. And you could perform nicely by putting a lot of modules of batteries together, which is very important when you want to use a car that runs on this. Your anode is the reductant. The electrochemical potential of the couple that is getting reduced and oxidized is called like mu A. This thing needs to be higher than the LUMO of the electrolyte, otherwise the electrolyte will reduce. You can tweak this thing by having a passivation layer, the solid electrolyte interface on top of this. The cathode is your oxidant, electrochemical potential mu C. It needs to be lower than the electrolyte LUMO, or otherwise it will oxidize the electrolyte. If you passivate the cathode at your own risk, you can tweak this potential. For electrochemical stability, the voltage at open circuit needs to be the distance between anode and cathode, but it needs to be lower than the electrolyte window. Otherwise, you're doing electrochemistry on the electrolyte. If this difference, so the difference between the window of anode and cathode and the window of the electrolyte is small, you can form these passivating layers on the two sides, which gives stability, so you don't keep doing electrochemistry on the electrolyte, but it can give some issues to like how much lithium are you actually able to bring around. So our nice arrangement of energy levels to remind ourselves this thing. Why do we use electrolytes that are organic? Because lithium plus is soluble in non-liquid electrolytes, and non-liquid electrolytes allow us to open up this window of the electrolyte. It's difficult to use pure lithium for your anode, so we tend to end up using composites of lithium. It's very nice to be able to have electrolyte interface stabilizing. It can solve a lot of problems, but also it's a very complicated thing to engineer, and it really forms by itself, and it's difficult to touch, and sometimes it can sequestrate a lot of the lithium that you want to use. The cathode needs to accommodate as much lithium as humanly possible, because you want this to be rechargeable, and the insertion, desertion needs to be within the solid, as your redox couple does the reaction. But you need to remember that the limit, if you're using oxides, is the 2p energy band. You don't want to do electrochemistry on oxygen, and then all the redox couples need to be higher than the 2 band and go like that. If you want some very nice literature, I recommend these 2 things. This is a Bible written by Goodenough himself, and this thing is a very recent review, so it's super recommended because it goes through a lot of this material in a nice way. And this brings us to the end of the lecture, and I will see you at the very at the real interactive point in which we can discuss some of these things. See you soon.